Okay, non-uniformly charged rod. And so let's say we have lambda is alpha absolute value of x. So if the rod is like this, this is, for these ones, I will actually get a straight out numerical answer instead of getting a general equation. So let's say I have -30 to 30 meters, and I want to get the voltage here in the middle, 2 meters away, and then 2 meters to the side. So with the voltage, it's actually easy not only to get the voltage here and here, but any random point. I can get the voltage like right here also. So we'll do all three cases, show you the setup of the integral. Okay, so I'm going to put the XY axis right here. I'm going to take a piece of the rod like that. Okay, so if I'm trying to find the voltage here, I'm going to say the voltage created by that piece, dq, dV is going to be k dq over r. Remember, voltage doesn't have any direction, so then I just worry about its magnitude. And then k dq is lambda dx over, and then the r equation is going to be square root of x squared plus 4. Right, so this one from here to here is going to be x. So square root of x squared plus 4. Okay, so then you put the lambda function for a non-uniform rod, whatever is given. So then you're going to say lambda is alpha absolute value of x, k absolute value of x. Then you can integrate that from 0 to 3 and then double it for the other side. So then the voltage will be 2k, since I'm doubling it, integral 0. Oh, the alpha is, lambda is alpha absolute value of x. So the alpha comes out also. So then I have x dx over square root of x squared plus 4 from 0 to 3. Right? X dx from square root of x squared plus 4 kx, k alpha x. So now we could also calculate for alpha, just like before. We need to know what the fudge factor is. So q is equal to integral lambda dx. Then you're going to have alpha x dx 0 to 3, and then double it. And then you have q is 2 alpha. Then you have x squared over 2, right? So 2 alpha x squared over 2 from 0 to 3. And then the 2 and the 2 cancel. Q is equal to alpha, and then 3 squared is 9. So alpha must be q over 9 in order for that distribution to describe this rod. So that's what the fudge factor is. So every time we see an alpha from now on, we can just put that. We don't have to keep doing that calculation. So we have V2 times 9 times 10 to the 9th. Then alpha is going to be q over 9. Okay, and then a q, let's give it the same. 10 nanocoulombs. I've been using that lately a lot, so let's just stick to that. 10 nanocoulombs over the 9, right? So 2k alpha, which is q over 9, and then whatever that integral gives us. Okay, so let's see here. x divided by x squared plus 4, and then to the power 0.5. Oops. And then from 0 to 3. Okay, 1.60555. So let's write that down. 1.605551275. Okay, so 1.605551275 times. Well, this is going to be easy. This is going to cancel this. The 9 is going to cancel 9. So just basically multiply this by 20. And V is going to be 32.111 volts. Right? So we could use the uniform charged rod, calculate that as a base of comparison. So either we can recalculate for uniform rod, or we can use the equation that we derived, the general equation for the voltage that we derived yesterday. So since we already have that derived equation, let's just use that, because I kind of want to use this. I kind of want to use the uniform one, and then I'm going to compare this to the uniform. So what was the general equation for the uniform? Was that the one that was sine hyperbolic? Oh yeah, it was sine hyperbolic, right? KQ over L sine inverse hyperbolic L over 2D. Was that it? Anyone have that from yesterday? For the general equation of a uniform rod at any distance from the center. Anyone have that?
Oh, Professor, you're missing a 2 at the front. You're missing a 2 at the front.
Oh, a double here, and that's it?
Looks like it.
Okay, cool. So now we could just put 2, 9, then we could 10 over the length is going to be 6 meters for the total length of the rod. Sine inverse hyperbolic 6 over 2, and then D is 2 meters. Okay. Okay, here we go. So sine inverse hyperbolic is right there. So 6 divided by 4 sine inverse hyperbolic times it's going to be 90. 2 is going to be 180 divided by 6, which was 30. Okay. So this gives me a good measure of comparison to see if this answer makes sense. So does that make sense now? If the uniform rod, which is equally charged everywhere, creates a voltage of 35 volts at that point, a charged rod, which is more charged towards the end, right, which is going to be farther away, right? So it should be slightly less voltage than the uniform. Yeah, it's good. Makes sense. Cool. So if my answer here was too much smaller than that, or if it was bigger than that, of course, bigger than that would be a real huge red flag. I would have to double check my steps here. Or something I've done wrong. But if it was like, let's say 15, that would also be a red flag because their total charge is the same of the two rods. So it can't be that much smaller than the voltage created by the same charged rod. You know, it's got to be smaller, but slightly smaller. Okay, makes sense. You see that? Okay, so now let's do 2 meters from the side. There, right there. Okay. 2 meters that way. And then we can also check with the voltage for the uniform. What is the equation for the voltage of the uniform on the side? We could do that first. Well, I think it was something like ln kq over L, ln of L plus D minus ln of D. Was it something like that?
Yeah, that's pretty much it.
Huh?
Yeah, that's it.
See, the only reason I remember those is because it was yesterday, fresh in my mind. And I kind of remember it as ln because when we took the derivative to check it, these ones came down, and then that gave us the electric field equation to check if the voltage makes sense. So now we can kind of put it here and get an expected answer. So this is 9, 10, 6, ln of 6 plus 2. So ln of 8 minus ln of 2. So that'll be ln of 4, basically. Okay. Okay, so we have ln of 4 ln, let's see, 4 ln times, that's 90 divided by 6, 20 volts. Now that in and of itself does make sense in a sense because remember the voltage drops quicker on the side than on this way. So if 2 meters up was 35 volts for a uniform rod, 2 meters to the side is less voltage. You see, so that already makes sense. So now if we do this answer, the non-uniform, is it going to come out more voltage or less voltage? Oh, I see, we have more charge here, but then we have very little charge here, but then we have more charge here. See, this has two competing things because some of the charge is very close to you, but then some of the other concentrated charge is far from you. But I believe it still comes out larger than the uniform. When we did it for electrical field, that's what happened, right? The non-uniform electrical field, because the fact that some of the charge is so close to you dominates over the fact that some of the concentrated charge is far away from you. So I think the answer should be slightly more than that, maybe 22, 23 volts. Okay, so then how do we set up this integral? We take a piece here, and then dv is going to be k dq over r, k lambda dx over, and then the r was, we've done that several times, right? What's the r in that situation on the side? It's L from here to here is x, from here to here is r, from here to here is L over 2, from here to here is D. So we say L over 2 plus D is x plus r. So r is L over 2 plus D minus x. So that's kind of the pattern always on the side. Okay, now we're ready to integrate that. So what should be the limit of your integral? Then we're going to put the lambda function, which is k alpha absolute value of x. Oh. Okay, let's see here. K alpha. So how do we integrate that? We got to integrate that -3 to 3. Yeah, because it's not symmetric. We can't go 0 to 3. I mean, the charge is symmetric, but the distance of this is further away, so it's not symmetric. So how would we do that? -3 to 3. Oh, because absolute value of x from -3 to 3, -3 to 0, absolute value of x is -x. So we probably have to split that into two integrals, right? So we have to say voltage is k alpha -3 to 0 -x dx over L plus 2. Oh, okay. What number does that become? 6 over 2 is 3. And then d is going to be what? 2 meters. Since we're getting a numerical answer here, d is 2 minus x. Okay, plus 0 to 3 x dx over x dx over 3 plus 2 minus x. All right, so that it's going to be k alpha. That's pretty much all, I think. You could take the negative to switch the order of the integral. The negative switches the order, so it becomes 0 to -3 x dx over 5 minus x plus integral 0 to 3 x dx over 5 minus x. We can't combine these, right? Yeah, we can't combine them. No. We got to do two separate integrals. Yeah, we got to do two separate integrals. Okay, so let's go to rule. So x over 5 minus x. Okay, from 0 to -3. Okay, let's write that down. .64998.185 plus then 0 to 3 of the same thing. 0 to just 3. See, it's a completely different answer. 1.58145. For 5366, let's say. Okay. So then the sum of these times k alpha, and then alpha was q over, we could just use the same thing that we had before, q over 9, right? So the alpha fudge factor doesn't change as long as we're keeping the lambda function the same, you see? And then k is going to be 9 times 10 to the 9th, and then q is going to be 10 times 10 to the -9, and then that's it. Okay, so as long as we just add these and multiply by 10, that's pretty much the answer. 0.64998 185 plus 1.58 145366 times 10. Slightly bigger than the uniform. Yes, yes, yes. Yeah, the uniform was 20. Yeah. Isn't that cool? Oh, man. How does that work? 22.3 volts. Nice. Many questions so far on those two, the center or the edge? No. Okay. Okay, how about some random point then? Like I said earlier, like let's say 2 and then 2 up. That voltage should be smaller than the 20, even the answer we got, the 22, right? So this one should be quite a bit smaller. So how do we set up somewhere random like that? With electric fields, we didn't do that because it was harder to do the directions and stuff, you know, with electric field. But with voltage, it's more doable. So what would be the coordinates of that point? So if this is from here to here is 3 meters, and this is -3. So the coordinates of that point would be, if it's 2 meters from the side, 2 and 2. So then that'll be 3 plus 2 will be 5. So 5, 2 meters, right? So then if I take a random piece, right, what would be that distance? So if you do dV is K dQ over R, that's the R. Let's see. So then from here to here is X, and then R is going to be this distance, right? So if this is 2, what's this distance going to be? Let's see, from here to here is X. From here to here was, this is 5. Oh, okay, so then this is 5 minus X. Let me see. So even though this is 2 meters from here, what matters is that this is 5 meters from here. Okay, so then from here to here is 5. Then from here to here is X. So then from here to here is 5 minus X. And then this is 2. So then R is going to be K lambda dx. R is going to be square root of 5 minus X squared. Okay. 5 minus X squared plus 2 squared, which is 4. Okay, and then you put the lambda function at that point. So then integrate. So voltage is equal to K alpha. Then you go from absolute value of X dx square root of 5 minus X squared plus 4, yeah, because 4 was 2 squared, right? Yeah, okay. 4, so -3. We probably have to be up, we have to break this down into 2 integrals again. -3 to 0 of negative X plus 0 to 3 of positive x. And then this negative changes the order of the integral again. Okay, so then you just have x now. So then you use that negative to change the order of the integrals. And then this is just going to be your 9, right? 9, this is 9. This is q over 9. Oh, and then it's just going to be 10. So then whatever we get here again, multiplied by 10. Okay, so this is probably the hard part, just setting up your correct r distance and then this distance. And then if it's if it's a function, in other words, if this function is an odd function, that means it's then you have to break up the integral 0 to -3. If your function here was x squared, then I could have just gone -3 to 3, because when you square a function, it doesn't matter if the number is negative. You see that? But if this is an odd function, then you have to do 2 integrals. Okay, so x over 5 minus x squared plus 4 to the power 0.5. Right? Okay. So 0 to 3. $1.27255. 1.27255. Okay, and then the other one, we go from 0 to -3. .6236394. Okay, so 0.6236394 plus 1.27255. Okay, times 10. Yep, 18 volts. See over here, if it was 22 volts, right? So here is 18 volts. Yeah, over there was 22, and then over here was, so remember, these are part of equal potential surfaces, like this. So this is an equal potential surface like this, an ellipse kind of, ellipse-looking equal potential surface. So here's 22 volts, and then this one is 18 volts, 18.96 volts. So then it's like this. And then this one we found out to be what? 32 volts, right? So 32 volts. You can see, yeah, so if we found the voltage there, it makes sense that it would be 18, smaller than the 22. Okay, those are all kinds of different rods that you can do, straight rods. Okay, so now let's do a bent rod into a semicircle. Okay.